Hi everyone. Today we're going to be completing our notes on 4.5 solving exponential and logarithmic equations using inverse operations. So the key idea for today is that we're going to use inverse operations to get the variable by itself. So similarly to any algebraic equation, we can use inverse operations to isolate the variable. So the example like x plus 3 equals 5. In order to solve for x, we subtract 3. We perform the inverse operation to addition by 3. Okay, that's because inverse operations undo one another, and we get the variable by itself. In the same way, exponentials and logarithms are inverses of one another, both the function and the operation. Therefore, if we perform both operations together, or if we compose those functions, then we get just the argument itself, or just the input to those functions, or just the variable. Okay, so the strategy that we're going to follow, step one, is to solve until you have b to the x is equal to a, or when you have log base b of x is equal to a. Okay, so what I mean by this is solve until you have that exponential or logarithmic expression or term by itself. Okay, so if there's any transformations, vertical stretches or compressions or vertical shifts, on the outside of those operations or outside of those functions, we want to undo those first using inverse operations to get these terms by themselves. Step two, once we have these by themselves in those forms, we're going to switch the form. So if it's a logarithm, switch it to exponential form. If it is an exponential, switch it to logarithm form. Okay. One quick note is that if you have a log, remember the domain for logarithms, the argument of the log must be positive. Okay, this is very important. Remember the domain for all logarithms, or I should say the parent functions for logarithms, is x greater than 0. Therefore, the inputs here, x, has to be greater than 0. The argument of the log has to be positive. No negatives, no zeros. All right, so let's go ahead and try a few problems. Example 1a. Here we have 4 plus 3 log base 4 of 2x equals 13. First thing we're going to do is try to get that log by itself. I'm going to subtract 4 from both sides, and we get 3 log base 4 of 2x is equal to 9. Okay? Dividing both sides by 3, getting rid of that coefficient, we get log base 4 of 2x is equal to 3. And now we've got the log isolated. So now we can rewrite this in exponential form. 4 to the third power is equal to 2x, and I'm going to carry my work up here. I know that 4 to the third power is 64 is equal to 2x. And finally, dividing both sides by 2, we get x is equal to 32. Now, in order to determine whether or not this solution is a true solution, we have to check and see if it's extraneous or not. This solution would be extraneous if it causes the argument of the log to be outside of the domain. Okay, so an extraneous solution is a solution that's not actually a solution to the equation. While algebraically we lead to that solution, it doesn't actually make the original equation, true. So always plug this back into the original equation and see if there's any domain errors or any conflicts with the argument of the log. So if we plug in 32 here, we get 2 times 32, which is a positive number. I don't have to know what that positive number is. It is 64, but all I need to know is that it's positive. Okay, there is no restriction here, or rather, there is no conflict to the domain here of the log. Therefore, this solution x equals 32 is a solution. Okay. 1b, this is a times symbol in between. Here we have 8 times 3 to the x equals 20. First thing we want to do is divide both sides by 8 to get that exponential term, or rather exponential factor by itself. So we get 3 to the power of x is equal to 28, which reduces to 5 halves. And then finally, we're going to rewrite this as a log. So log base 3 of 5 halves is equal to x. Now 5 halves is not a perfect power of 3, and so we have to use our calculator in order to solve this. So head over to your calculator, open up a new document. Once you do, we're going to start a new log. log base 3 of, I'm going to do control divide, 5 halves. And I'm going to hit control enter to get a decimal approximation. I get 0.834. So x is equal to 0.834. Now, I know that this is a solution because our original equation is an exponential equation. Remember, the domain for exponential functions is all real numbers. So any solution for x in an exponential equation is going to be a solution. Letter C. Here we have two logs and we're taking the difference of them. I notice using our quotient rule that we can combine these into a single log. So I'm going to write this as log base 5 of the numerator, 7x minus 3, over the denominator, 2x plus 1. And that's equal to 0. I also know that if we've got our log by itself now, so we can rewrite this using an exponential equation. So 5 to the 0 is equal to 7x minus 3 over the quantity 2x plus 1. Okay. We know that anything to the 0 power is 1, so this is equal to 7x minus 3 over 2x plus 1. And then finally multiplying both sides by 2x plus 1, we get 2x plus 1 equals 7x minus 3. Subtracting 2x from both sides, we get 1 is equal to 5x minus 3. And finally adding 3 to both sides here, we get 5x is equal to 4, or x is equal to 5/4, dividing both sides by 5. Okay? Oh, I'm sorry, 4/5, dividing both sides by 5. All right, so x is equal to 4/5. Now we have to go back and check whether or not this is extraneous. If I plug in 4/5 here, is 7 times 4/5 and then minus 3 greater than 0? I'm actually going to write this step out because I can't see just visually looking at this. 7 times 4/5 minus 3, is that greater than 0? Well, 7 times 4/5 is 28/5, and then minus 3 is greater than 0. I can already now see that this is true, but if you wanted to take it one step further, this would be 28/5 minus, this would be 15/5, and then I can see that this is 13/5. All right, so that first argument is fine. That is greater than 0. Let's check the second, 2x plus 1. Well, if we're going to multiply a positive number times 2, that's going to make it even more positive, a greater number. And then if we add 1, it's going to make it even more positive. So right now I can see that this is going to be positive because our solution for x is positive. Okay. If you wanted to test it out, you could plug in 2 times 4/5 plus 1 is greater than 0. You have to go down and check. So this would be 8/5 plus 1. 8/5 plus 1 would be 18/5. So yes, this is true. All right, letter D. Again, I noticed that we have the same logarithmic base, so I can combine these using the product rule. Log base 2 of x times a quantity x minus 2. All right, so now that we have the log by itself, we get 2 cubed is equal to the argument of the log, which I'm going to go ahead and distribute. Okay. Once we have this here, we have 8 equals x squared minus 2x. Subtracting 8 from both sides, we get x squared minus 2x minus 8 equals 0. And I know that this can be factored into the quantity x minus 4 and x plus 2 equals 0. And so that gives me solutions x equals 4 and x equals negative 2. If we plug both of these into the arguments of the logs here to check if it's extraneous, plug in 4. 4 is a positive number that works over here, but we also have to check over here. 4 minus 2, also positive, so 4 checks out. If we plug in negative 2 here, if we plug in negative 2 into this x, it causes this argument to be negative. Therefore, the solution x equals negative 2 is extraneous. We eliminate that solution. So this equation has exactly one solution, x equals 4. Letter E. Natural log of 2x minus 3 equals 21. I know that the base of the natural log is e. This is already isolated, the natural log. And so we have e to the 21st power is equal to 2x minus 3 when we rearrange, when we switch forms. So then we add 3 to both sides, and we get 2x is equal to e to the 21 plus 3. And finally, dividing both sides by 2, we get x is equal to e to the 21 plus 3 all over 2. All right, so this would be the exact answer. Let's go ahead and get a decimal approximation. Control divide, e. I'm going to actually use the e here. If you just type in the letter e, your calculator is going to try to think that's a variable. So make sure that you use the mathematical constant e here. So e to the 21st, and then plus 3, and that's divided by 2. Control enter. That's going to give us a pretty big number. So this looks like it is 659 million. I'm going to use some scientific notation. Times 10 to the 6th. Okay. Now let's check if this is extraneous. If I plug in this really gigantic 6 million figure into the natural log, is that going to be positive? Yes. If I double 6 million, you get 12 million minus 3. That's still going to be in the 12 millions. So this is going to be a positive quantity. Okay. Letter F, I notice that we've got some natural logs all across the equation here. So I notice that these first two terms are the product rule, so I can multiply those arguments. And then let's go ahead and move this over to the other side as well. So subtracting natural log of 2 from both sides, that gives us our quotient rule. Okay, so this would tell us that we have the natural log of the quantity x times the quantity x plus 1 all over 2 is equal to 0. Okay. So we are combining these two logs, the arguments, and then we're also subtracting the natural log of 2 to create one log here. So this is e to the 0 is equal to x squared plus x all over 2. We get e to the 0 is 1, and I'm going to also multiply that by 2. And so we get 2 is equal to x squared plus x. And so we get x squared plus x minus 2 is equal to 0. This factors to x plus 2 and x minus 1. So we get solutions -2 and 1. Okay, we have to check both. So -2. If I plug in -2 in for this first natural log, it's going to be a domain error, so we eliminate that solution. It's got to be positive. Plugging in 1, that's totally fine for any of these logs. We get 1 here, 2 here, and 2 here. This is a constant. So 1 is a solution. Letter G. 8.4 times 10 to the 5x equals 76. So dividing both sides by 8.4, we get 10 to the 5x is equal to, let's see, 76 divided by 8.4 is about 9.048. Okay. And then finally rewriting this as a log, I know that we're base 10, so I'm going to write this as the common log of 9.048 is equal to 5x. Okay, and then dividing both sides by 5x, divided by 5, I mean, we get x is equal to the log of 9.048 over 5. All right. And let's see what that is. I'm actually going to go ahead and plug it in as an exact answer. So I'm going to do log base 10 of control divide. We have our 76 divided by 8.4, and that's all over, that is all over 5. So actually that gives us a decimal approximation of about 1.91. I'm sorry, 0.191. Okay. This is an exponential equation, so domain is all real numbers. So this solution is not extraneous. Letter H, dividing both sides by 9.21. We get 5 to the 7.1x is equal to, I'm actually just going to round at the very end. We'll keep our answers exact until the very end. Rewriting this in log base 5 of 28.4 over 9.21 is equal to the exponent 7.1x, and then finally dividing both sides by 7.1, we get x is equal to, head over to our calculator, there we go, control enter, there we go, 0.9899. 0.099. Okay. And again, an exponential equation, so this is the solution. Okay. Flip the page, let's get some more practice. So solving for the 4 to the x, we're going to divide both sides by 6. 4 to the x is equal to 31/6. And then rewriting log base 4 of 31/6 is equal to x. And so then we plug this into our calculator. Log base 4 of 31/6, 1.185. And that is a solution. Okay. Number 2, here we have two log base 7s equal to one another. Now, there's a trick that you could do here. You could subtract one of the log base 7s from one side to the other. I also noticed that if we were to rewrite this whole equation using exponentials, we would just get that the arguments of the logs are equal to one another. I'm going to show the first method because if you didn't recognize that second method right away, that's totally okay. But let's go ahead and write this out. So this would be log base 7 of 6x plus 4 divided by the quantity negative 3x minus 5 is equal to 0. Okay, and then we would get 7 to the 0 is equal to 6x plus 4 over negative 3x minus 5. And then this quantity, 7 to the 0, is equal to 1. And so then what we get is multiplying both sides by negative 3x minus 5. We get that the arguments of those original logs are equal to one another. Adding 3x to both sides, we get 9x plus 4 is equal to negative 5. Subtracting 4, we get 9x is equal to negative 9. And then dividing both sides by 9, x is equal to negative 1. If I plug in negative 1 here, well, let's see what happens. Over here, we have positive 3 minus 5, so that would be a negative argument. So this would not be a solution. And in fact, this also does not work in this other equation, this other argument as well. 6 times negative 1, and then plus 4 is negative. So because all of our solutions are extraneous, this equation has no solution. All right. Number 3, here we have 2 log base 2. We're going to combine those using the product rule. So we multiply x times the quantity x minus 4. I went ahead and multiplied that out. We get 2 to the 5th is equal to x squared minus 4x, or 32 is equal to x squared minus 4x, or x squared minus 4x minus 32 is equal to 0, subtracting 32 from both sides. This factors to x minus 8 and x plus 4 equals 0, x equals 8, x equals negative 4. Checking each of these, well, I know the negative 4 doesn't work because of that first log. 8 works just fine in both of those logs. So the solution, x equals 8. Number 4, dividing both sides by 3.21. We get 54 to the 6.7. X is equal to 89.01 over 3.21. Rewriting log base 54 of 89.01 over 3.21 is equal to 6.7x. So then x is equal to 1 over 6.7 times the log of 89.01 over 3.21. Okay, this would be the exact answer. You could put this whole thing over 6.7. I'm just showing you another form of what this might look like. Go ahead and plug this in your calculator, get a decimal approximation. And so we have 1 over 6.7, and then times the log base 54 of 89, control divide, 89.01 over 3.21. Control enter, 0.124 looks like. X equals 0.124. This is an exponential equation, so domains are all real numbers. That's the solution. Okay, number 5. We have log base b now, so the base is a variable. We'll see how that actually doesn't matter in this case. Okay, so log base b, here we have log base b of x squared using that power rule. We'll move that up here. And you know what? Let's go ahead and also do the quotient rule. So over 2. And then that's equal to log base b of 2x minus 2. So like we saw before in number 2, if we have two logs with the same base equal to one another with nothing attached on the outside, those arguments are equal. So x squared over 2 is equal to 2x minus 2. Multiplying the whole equation by 2, we get x squared is equal to 4x minus 4, or x squared minus 4x plus 4 is equal to 0. This is a perfect square trinomial, so x minus 2, the quantity squared, equals 0. We have the solution x is equal to 2. If we plug this into the original equation, we find that this is fine. There's no domain error here. 2 is positive in each of these arguments here. All right, so number 6. Again, two logs of the same base equal to one another. We have x plus 1 equals 2x minus 2. Subtracting x and then adding 2, we get 3 equals x. Okay. Let's see. 3 plus 1, that's positive. 2 times 3 is 6 minus 2, also positive. So 3 is a solution. Nice. That one was quick. Number 7, dividing both sides by 8.4. I feel like we did this one already. This one is the exact same as earlier. So we're going to skip. So same as, let's see, what number is that? That is example 1G. Okay. Let's see, number 8. So using our power rule, and then we're also going to use the product. So we have log base 3 of 5x squared is equal to log base 3 of 14x plus 3. Again, two logs of the same base equal to one another. 5x squared is equal to 14x plus 3. Setting everything equal to 0, we get 5x squared minus 14x minus 3 equals 0. This factors to 5x, let's see, plus 1 and x minus 3. So we get solutions. X is equal to negative a fifth and x is equal to 3. Let's check both of those. If I plug in negative 1/5, that fails this log right here. So this is extraneous. If I plug in 3, it passes here. That's a constant, and it passes here. 14 times 3 plus 3 is positive. All right, we got a couple more for today. Number 9, we want to get the natural log by itself. First thing we're going to do is subtract 2 from both sides. 2 natural log is equal to negative 1. And then dividing both sides by 2, we get natural log, oops, I forgot my argument, natural log of x equals negative 1/2. So that tells us rewriting e to the negative 1/2 is equal to x. Okay, so this is equal to 1 over e to the positive 1/2, or the square root of e, which, if we rationalize this, this is root e over e. Okay, the square root of e over e, e is a positive number, so the square root is also positive, and then divided by a positive is positive. So this is a solution. Okay, last one, e to the 2x equals 20. We have the natural log of 20 is equal to 2x. Okay, dividing both sides by 2, we get x is equal to natural log of 20 over 2. And back to our calculator. Control divide. Natural log of 20 over 2. We get 1.498. Okay, this is an exponential equation, so that is a solution. All right, so this was a lot of practice. We're going to get more on this, solving exponential and logarithmic equations using inverse operations. So we'll see you tomorrow in class. Have a great day, everybody. Goodbye.